Welcome back to the deep dive. We love looking at those real turning points in science, the ideas that just shift everything.
Definitely, those foundational moments.
Exactly. And Aryabhata's system in Indian astronomy, that was certainly one of them, a huge leap.
Absolutely massive.
But as we always see, right, the first big idea is never the whole story. It's just the beginning.
It kicks things off.
What comes next is often this, well, fascinating process of digging in, asking questions, maybe pushing back a little, and definitely building on it.
And that's precisely what happened in India after Aryabhata published his work. It wasn't just accepted passively. Far from it.
So it wasn't like, okay, new system, everyone use this now.
Not at all.
Yeah.
It sparked this incredibly vibrant period, a lot of intense intellectual activity surrounding his ideas.
Okay, so that's what we're diving into today. What happened after Aryabhata?
Exactly. We'll explore this really interesting landscape. We'll look at the commentators. They were crucial, actually, who helped unpack his, well, often very concise verses.
Right, the sutra style, very dense.
Incredibly dense. And then there were the debates. Real energetic arguments, even some major controversies that popped up.
Controversies, interesting. About what?
Oh, fundamental things.
Yeah.
We'll get into that. And how all this, discussion and disagreement eventually led to different schools of thought forming, distinct traditions within Indian astronomy.
Wow, okay, so it wasn't just one monolithic thing.
Not at all. And this whole period, it just perfectly shows a mature scientific tradition,
Yeah.
one that's constantly refining itself through rigorous debate, through exploring different angles. It's about the process.
Okay, let's start there then. With Aryabhata's work itself, the Aryabhatiya, you mentioned it was in these really short, concentrated verses, almost like code.
That's a good way to put it. The sutra style is extremely economical with words. It lays out principles, results, algorithms, but often without extensive proofs or explanations.
So how did people, centuries later actually figure out the nuts and bolts? How did they learn to use his system properly?
Yeah, that's the key question. And the answer lies in the tradition of bhāṣya, commentaries.
Okay.
These were absolutely essential. Think of Aryabhata's verses like maybe the core equations or theorems. The commentaries are the textbooks that explain them, provide the proofs, give examples, show how to apply them.
So they weren't just translations.
Oh, much more than that. They were deep dives in themselves. They unpacked the underlying geometry, which Aryabhata might have just assumed. They demonstrated the algorithms step by step. They even justify the specific numbers, the parameters he used.
Okay, so who are these commentators? Any key figures we should know?
Definitely. One of the most important early ones is Bhaskara I. He lived in the 7th century, a couple of centuries after Aryabhata.
Bhaskara first, got it.
His commentaries on the Aryabhatiya are just invaluable. They give us tremendous insight into how Aryabhata's work was understood and elaborated upon relatively early on.
And what kind of things did Bhaskara focus on in his commentary? Was it just math?
A lot of it was mathematical elaboration, yes.
Yeah.
Explaining the geometry, deriving the formulas. But he also tackled the more conceptual aspects. For instance, Aryabhata's idea of the Earth rotating on its axis.
Ah, yes, the rotating Earth. That must have been a tough sell back then.
He was definitely radical for the time. And commentators like Bhaskara, I didn't shy away from it. They actually provided arguments, mathematical and logical, to defend this idea, to show why it made sense within Aryabhata's system.
So the commentators weren't just explaining, they're also advocating, defending the controversial bits.
Precisely. They were active participants in shaping how Aryabhata's legacy was perceived and understood. They were filling in the gaps, yes, but also reinforcing the coherence and the correctness of the system as they saw it. They were crucial for its transmission and acceptance, or at least its serious consideration.
It makes you wonder, doesn't it? Without these commentaries, would Aryabhata's work have been harder to understand, maybe some nuances lost?
Oh, undoubtedly. The conciseness of the sutra style means there's a lot of assumed knowledge. Without the bhāyas to bridge that gap, to spell things out, it's very likely that the transmission would have been much weaker, perhaps more prone to misinterpretation.
So they acted like a vital bridge across time.
Exactly. Connecting Aryabhata's initial insights to later generations of scholars, they ensured his work wasn't just a historical artifact, but a living tradition to be engaged with, debated, and built upon. We really rely on them today to understand the depth of his thought.
Okay, so the commentaries helped explain and defend. But you mentioned controversy. Not everyone just accepted these explanations, right? Science thrives on skepticism, after all.
Absolutely, and that's exactly what we see. Aryabhata's ideas, even with brilliant commentators like Bhaskara I explaining them, were definitely not universally accepted overnight. They sparked some really significant debates, major disagreements.
Let's get into those. What was the biggest point of contention? Was it the Earth's rotation?
That was certainly a major one, yeah. It remained controversial for a long time.
Who was leading the charge against it?
Well, one of the most prominent critics was Brahmagupta.
Brahmagupta, another huge name in Indian astronomy and mathematics.
A giant, yes. And he lived a bit after Bhaskara I in the 7th century as well, but represented a different perspective. He vehemently rejected the idea of Earth's axial rotation.
Vehemently? Why? What were his arguments?
He used what seemed like common sense physical arguments, based on observations from right here on the ground.
Like what?
Like if the Earth is spinning really fast, wouldn't a bird flying in the air get left behind? Or if you shoot an arrow straight up, wouldn't it land somewhere else because the Earth moved under it?
Oh, okay. The pre-Newtonian physics perspective, it makes intuitive sense if you don't have a concept of inertia or relative motion.
Exactly. From the physics of the time, or rather, the intuitive understanding of motion, these seem like very strong objections. Why don't we feel a constant wind? Why don't buildings crumble?
Right. So what was the alternative explanation then for why the stars seem to move across the sky every night?
The more traditional view, which Brahmagupta seemed to favor, often involves something called the Pravaha wind.
Pravaha wind.
Yeah, a sort of cosmic wind, a hypothetical force that was thought to sweep the entire celestial sphere, all the stars, planets, the sun, the moon, around a stationary Earth.
So the whole sky moves, not the Earth.
That was the idea.
Yeah.
So you had these two fundamentally different pictures. Aryabhata saying the Earth spins, explaining the daily motion that way, and the more traditional view, defended by people like Brahmagupta, saying no, the Earth is still, and this cosmic wind moves everything else.
A real clash of fundamental models.
A very deep disagreement about the basic structure of the cosmos. It shows how challenging it was to shift from that firmly ingrained geocentric perspective.
Okay, besides the Earth's rotation, what other major debates flared up? Surely that wasn't the only thing they argued about.
No, definitely not. Another huge area of debate was the fundamental astronomical parameters themselves, the actual numbers used for calculations.
What kind of numbers?
Things like how many times does Jupiter orbit the sun in a specific vast period of time, like a yuga? Or what is the precise length of a year down to the fractions of a day?
The core constants, basically.
Exactly. The constants that underpin all the calculations. And Aryabhata's values for these constants, well, they often differed from those used in older, highly respected texts, like the Ārya-pakṣa.
The Ārya-pakṣa being a sort of benchmark text.
A very influential one, yes. Considered quite authoritative by many. And Aryabhata's numbers also differed from those proposed by contemporaries, including Brahmagupta again.
So Brahmagupta didn't just disagree on the Earth's rotation, but also on the basic numbers.
Correct. He proposed his own set of parameters in his work, the Brahma-pakṣa. And these differences weren't just, minor quibbles.
Why not? What was the impact of using slightly different numbers for, say, the length of the year?
Well, think about predicting eclipses or the position of Mars decades or centuries from now. Even small differences in your starting parameters, your fundamental constants, they get magnified over time.
Ah, I see. So using Aryabhata's numbers versus Brahmagupta's numbers could lead to noticeably different predictions down the line.
Precisely. Your prediction for the timing of an eclipse or where exactly a planet would appear in the sky could be quite different depending on which set of constants you plugged into your calculations.
And how did they try to resolve these differences? Was it just about whose authority you trusted more?
Authority played a role, sure, but it wasn't just that. Astronomers would compare the predictions generated by the different sets of parameters against actual observations. Which system seemed to match reality better?
So there was an empirical element, testing against observation.
Yes, within the limits of the observational tools they had, of course. They didn't have telescopes. But they had instruments like gnomons, armillary spheres, water clocks. They could measure angles, track positions, time events. And they would debate which mathematical model and which set of underlying numbers best fit the data they could gather.
That sounds like a genuinely scientific process. Observation, prediction, comparison, debate.
It absolutely was. It shows a commitment to finding the most accurate description of the cosmos, driven by both mathematical reasoning and empirical checking. The debates over parameters were intense because the accuracy of their calendars and predictions depended on getting those numbers right.
Okay, rotation and parameters. Any other big areas of disagreement? You mentioned yugas earlier.
Ah, yes. The structure of cosmic time itself. This was another significant point of departure for Aryabhata.
How so?
Well, the traditional Puranic view of cosmology, which was widely known, described these vast cosmic cycles, the yugas, as being of unequal length.
Unequal?
Yeah, in a specific ratio, 4.3.2.1. The Katha Yuga was the longest and most virtuous, then the Treta, Dwapara, and finally the Kali Yuga, the shortest and most degenerate age, which was considered the current one. It represented a cosmic decline.
A kind of entropy built into the time cycle.
You could sort of see it that way, yes.
Yeah.
It was a deeply embedded cosmological and philosophical idea. But Aryabhata, he proposed something quite different.
What did he propose?
He proposed yugas of equal duration, symmetrical, mathematically much cleaner.
Equal yugas. Why? Was it just for mathematical convenience?
That seems to have been a major motivation. His entire system aimed for a certain mathematical elegance and internal consistency. Having equal yugas simplified calculations involving planetary mean motions and revolutions over these vast timescales considerably. It fit neatly into his computational framework.
So it made the math work better within his system.
Yes. And commentators like Bhaskara I, whom we mentioned earlier, explicitly defended this equal yuga structure. They argued it was necessary for the coherence of Aryabhata's specific astronomical model.
But that must have clashed pretty hard with the traditional 4.3.2.1 idea.
Oh, absolutely. It was a direct challenge to a very established cosmological view, and predictably others pushed back.
Including Brahmagupta again?
Including Brahmagupta. He adhered firmly to the traditional, unequal yuga structure described in the Puranas and other texts. For him, and likely for many others, the traditional cosmological framework held precedence over Aryabhata's mathematical streamlining in this specific area.
So again, we see this tension. Aryabhata pushing for mathematical consistency, perhaps, and others defending tradition or alternative models.
Exactly. These weren't just minor disagreements, they touched on fundamental assumptions about how the universe worked, the nature of time, the validity of different sources of knowledge, mathematical coherence versus traditional authority.
And all this debate, all these different viewpoints on rotation, parameters, yugas, did this lead to fragmentation or something else?
It led to something really interesting. The formation of distinct schools, or maybe computational traditions is a better term. They were known as pakas.
Pakas, okay, like different camps.
Sort of, yeah. Think of them as distinct lineages of astronomical practice and calculation, often tracing their core principles back to either Aryabhata or Brahmagupta.
So what were the main ones?
The two most prominent that emerged over time were the Ārya-pakṣa and the Brāhma-pakṣa.
Makes sense, following Aryabhata and Brahmagupta.
Exactly. The Ārya-pakṣa generally followed the parameters and methods laid out by Aryabhata, though with some internal variations. For instance, some later astronomers in this tradition adopted a midnight epoch, the starting point for daily calculations, instead of Aryabhata's original sunrise epoch.
Why is the change to midnight?
Practical reasons, perhaps? Easier for certain types of observations or calculations, maybe aligning with practices in other regions. It shows there was evolution even within a school.
Okay, and the Brahma-pakṣa?
They naturally followed the system and parameters established by Brahmagupta in his Brahma's Fusihanta. This included his specific values for planetary revolutions, year length, and his adherence to the traditional yuga structure and a stationary Earth.
So you had these parallel traditions developing. Were they completely separate? Like, if you were Ārya-pakṣa, you ignored everything from the Brahma-pakṣa.
Not necessarily that rigid. It wasn't like signing up for a club and refusing to talk to the other side. We do see evidence of astronomers being aware of both systems.
Oh, how so?
Sometimes they might calculate something using both sets of parameters, maybe for comparison, to see how the results differed. Or they might try to synthesize ideas, taking elements from both traditions. It wasn't always strictly one or the other.
So more like preferred toolkits, perhaps.
That's a decent analogy. They represented distinct intellectual lineages, often passed down through teacher-student relationships. They had their preferred constants, sometimes slightly different algorithms, different ways of approaching problems. And as we discussed, these differences would lead to diverging predictions over the long term.
Which would then maybe fuel more debate and observation.
Exactly. It created this environment where different approaches coexisted. It allowed for both continuity, faithfully transmitting the methods of, say, Aryabhata, and also for localized innovation, as astronomers within a pakṣa might refine or adjust specific aspects of their tradition.
It sounds counterintuitively, maybe, like having these competing schools was actually healthy for the development of astronomy.
I think that's a very fair assessment. This period, with all its debates and the formation of these pakas, wasn't a sign of stagnation at all. Quite the opposite. It was an era of intense intellectual refinement.
How so? Because they had to defend their positions.
Precisely. If you wanted to defend Aryabhata's system, especially the controversial parts like Earth's rotation or equal yugas, you couldn't just say Aryabhata said so. You had to provide stronger mathematical proofs, better logical arguments, maybe try to find observational evidence.
And similarly, if you were proposing alternative parameters, like Brahmagupta did,
You had to justify them. You had to show, perhaps through calculation or observation, why your numbers were better, why they led to more accurate predictions. This constant need for justification pushed for greater rigor all around.
so the debates forced everyone to sharpen their arguments and methods.
Exactly. And the commentaries, as we said, played a huge role in deepening the understanding of the foundational texts. They were just passive summaries. They were active engagements, interpretations, justifications.
Did the debates also push for better observations?
It likely did, yes. When predictions from different systems diverged, the obvious way to try and settle the matter was to go out and observe, to see which system matched reality more closely. Now, the progress in observational instruments was gradual, but the impetus to observe carefully and critically was certainly fueled by these theoretical disagreements. They were trying to improve computational techniques as well.
So it was a cycle. Theory leads to debate, debate pushes for better observation and math, which feeds back into theory.
A classic scientific feedback loop, yes, operating over centuries. The back and forth between the ideas of Aryabhata and Brahmagupta, filtered and amplified through generations of commentators and practitioners within their respective pakas, demonstrates a really mature scientific culture.
Mature in what sense?
Mature in its commitment to scrutiny, to logical and mathematical justification, and to, as best they could, empirical validation. It wasn't just about accepting authority. It was about testing, refining, and debating to reach a better understanding of the cosmos.
And this vibrant period, this tradition of commentary and debate, it didn't just fizzle out, did it? We see echoes of it much later.
Oh, absolutely. It laid the essential foundation for later developments, most famously, the incredible work that came out of the Kerala School of Astronomy and Mathematics, centuries later.
Ah, Kerala. We've touched on them before. How did this earlier period connect to their work?
Well, many key features in the Kerala School explicitly saw themselves as working within the lineage of the Ārya-pakṣa.
Really? So they identified with Aryabhata's tradition.
Yes. For instance, Nīlakaṇṭha, a major figure in the 15th century.
Right, Nīlakaṇṭha, known for his Tychonic-like model.
Exactly. He wrote an extensive and highly influential commentary on Aryabhata's Aryabhatiya. He was directly engaging with and building upon that foundational text hundreds of years later. He clearly saw himself as continuing that specific intellectual trajectory.
So there's a direct line of transmission and engagement.
A very clear one. And Nīlakaṇṭha didn't just comment, he innovated significantly within that framework. His development of a revised astronomical model, a geo-heliocentric system where planets orbit the sun, which then orbits the Earth, was a major theoretical step.
A step seemingly taken within the Ārya-pakṣa tradition?
Yes, and think about Mādhava, another towering figure from Kerala, slightly earlier than Nīlakaṇṭha.
Mādhava and the Infinite Series. Amazing mathematical work.
Truly groundbreaking work on infinite series for trigonometric functions like sine and cosine. This incredibly sophisticated mathematics can be seen as a direct continuation of the strong mathematical emphasis that characterized Aryabhata's original work and the subsequent tradition that valued mathematical rigor and innovation.
So the seeds of Kerala's mathematical breakthroughs were sown, in a way, back in this earlier period of commentary and mathematical focus.
You could definitely argue that.
Yeah.
The Kerala school wasn't just a sudden, isolated burst of genius. It emerged from this long, rich tradition that had spent centuries grappling with Aryabhata's legacy, debating his ideas, refining mathematical techniques, and maintaining distinct schools of thought that fostered both continuity and innovation.
It really paints a picture of a long-term evolving scientific enterprise.
It does. It shows the longevity and the sheer innovative power that can come from centuries of sustained critical engagement with foundational ideas and ongoing debate among different viewpoints.
Okay, so let's try and pull the main threads together here. What we've really seen is that Aryabhata's work, while absolutely foundational, was really just the starting gun.
Right, the beginning of a long conversation.
And what followed was this incredibly dynamic period in India. You had commentators playing this essential role, not just preserving his ideas, but actively explaining, justifying, defending them, making them accessible.
Crucial work. The Balayas were key.
And then the debates, the healthy skepticism, the disagreements, like the big one between Aryabhata and Brahmagupta over Earth's rotation, over the fundamental numbers, even over the structure of time itself.
Yeah, that critical engagement was vital. Brahmagupta's criticisms, even if ultimately proven wrong on some points by later physics, were important challenges that forced deeper thought and justification.
And all this led to the formation of these different schools, the pakas, primarily the Ārya-pakṣa and the Brāhma-pakṣa, competing but also interacting traditions.
Which allowed for different approaches to be explored and refined over time. It wasn't monolithic.
And the whole picture really reveals a scientific tradition that was, deeply invested in mathematical rigor, in logical argument, and in striving for an accurate understanding of the universe using the tools and observations they had.
Absolutely. It was a process of continuous refinement, driven by commentary, debate, and a persistent quest for better cosmic models.
It really is fascinating. It makes you think, doesn't it, about how science works even today. We still build on foundational work. We still have commentaries, in a sense, interpretations, textbooks, review articles.
That's true. The forms change, but the function is similar.
And we certainly still have debates, controversies, competing theories, or interpretations of data, different schools of thought in many fields.
We definitely do. Think about debates in cosmology or quantum physics interpretations, or even climate modeling. There are often different camps, different approaches.
So maybe these patterns we see from centuries ago in India, the interplay of foundational work, commentary, debate, competing viewpoints, perhaps they're just fundamental to how scientific knowledge progresses, period. How we collectively argue our way towards a better understanding.
It certainly seems like a recurring pattern in the history of science. That process of discussion, disagreement, and refinement seems essential. It's rarely a straight line.
Something for us all to think about, perhaps, as we watch scientific debates unfold today. How much of it echoes these ancient patterns?
A very interesting thought to end on.
Indeed. Well, that wraps up our deep dive for this time. Join us again as we continue exploring the fascinating history of ideas.